I'm Emma Landsiedel.
I'm Jared Hout.
And this is Lab 10 on laser cavities. The purpose of this experiment was to align this mirror with the laser cavity to allow this laser to laze. So we used this guide laser to set up this mirror so it was parallel to the rest of the optical system and make it parallel to this mirror. This was done by adjusting these different knobs, and then we were able to laze. We were able to get a 0-3 mode on this, and this can be changed by adding or decreasing loss to the system as shown.
The mode can be changed by adjusting the tip and tilt of the mirror, by changing the cavity length, or by introducing a barrier into the cavity,
which increases loss.
This window is slanted to achieve Brewster's angle, which allows all the P polarized light through and most of the S light to reflect off. So if N is 1.5 on it, the Brewster's angle is about 56.3 degrees. And the polarization is linear, we know, because it's P polarized. We found that the polarizer was oriented horizontally. All of that light came through. And when it was vertically, all light didn't go through, showing that the P polarization, which is horizontal, was. The purpose of this experiment was to determine the free spectral range, or FSR, of the Heaney laser. We did that with 3 methods. One was using a Fabry Pro Etalon and the oscilloscope. One was using the electronic spectrum analyzer and photodetector. And the last was using the formula C/2L to find the FSR. And those should all 3 be the same based on the formula.
This is the output from the ESA, and it shows that our beat frequency is 552 megahertz. The scanning Fabry Pro has its own FSR. This creates a repeating pattern on the oscilloscope, and since we know the FSR of the Fabry Pro and can find the relative FSR of the light using the oscilloscope, we can find the actual FSR of the light to describe its spectrum.
Using the 3 methods, we found different FSR measurements of 552 megahertz, 519.5 megahertz, and 461.54 megahertz. This one's smaller because our L value should be a little bit smaller than what we measured.
The polarization state is the same as in Part A, as we can see from rotating this polarizer. The purpose of this experiment was to profile the beam of a Heaney laser using its commercial beam profiler. So with this, we'd find the divergence angle, the numerical aperture, the location of the beam waist, and the size of the beam waist in the X and Y direction.
Because this is a Gaussian beam, we expect to see a more quadratic model near the beam waist where it'll diverge more quickly, and a linear model farther away where it'll diverge more slowly.
We moved the beam profiler along the rail to get the X and Y radius at different locations, and we found that to be a linear regression. So that means that we are too far away along this rail from the beam waist to get any quadratic, so we had to use this equation instead of our quadratic model to find the beam radius.
We used our linear model to find the distance from the beam, this distance from the optical rail that our beam waist was, which puts it right in front of the laser. And then we used our slope to find the divergence angle, and the numerical aperture is shown here. And then we finally used that equation to find our beam waist size, which is about half of what the published diameter is.
These are the linear models that we use. The top is X and the bottom is Y.
Overall, we learned about polarization states, alignments, FSR, and beam profiles, which are the defining characteristics of lasers.